lines, right? If Q is here, we get this line. If Q is here, we get another secant line, right? So it depends on the position of Q. Depends on the position of the Q. That's why, so we get a family of functions. So the secant lines get this. So now we don't have a second point. So how are we going to find the slope of only one point? So this is a phenomena of the idea of limits. So what do? We do this. We're going to take the limit. We're going to take the limit. Then we let the Q point going to be P point. So Q approaches to P. You see this picture? Imagine Q is here, and the second picture is Q is getting closer and closer to Q is getting closer and closer to P. Then we take a limit. We let the Q point to be the PQ point. We use the idea of limit. You see? Well, if Q is here, of course, we have this kind of secant line. Q is here, we have this secant line. So in any case, doesn't matter where Q is. We let Q approach to P. The top three, Q approaches P from the right-hand side, right? The bottom three, Q approaches P from the left-hand side. So think about the ideas of limit. We have a right limit, we have a left limit. So we use the idea of limit. Okay, now let's take the slope at the point P. So how do we do that? We take the limit, we let the x value, which is Q, which is x in Q, in point Q. Okay, so the point Q is x squared, right? So let the x value for point Q approach to 1, right? And then, of course, x squared will approach 1 also. So we let this point Q approach to P, and finally to BP. That's the idea of limits. We take a limit. We say let x approach to 1. We simplify this rational expression function, so we get x plus 1. Now we have no problem to plug in. So if x is 1, so 1 plus 1 get a 2. So the slope at a point P, at this point P is 1, 1. You see, fantastic, right? Give us 1 point, we can use the limit idea to find its slope of the tangent line at this point. So this is one way to use the idea of the limit. All right. So before we use 2 points to find slope of a line, but now we only need 1 point to find the slope of the tangent line. The condition is it has to be tangent. This line is tangent to the function. Tangent to the function. If anyone has any questions, feel free to stop me at any time. All right. So, and of course, you can see the 2 points, right? Which is we have y2 minus y1, x1 minus x2, x2 minus x1. It's still the idea of the slope. So now let's make a definition. The tangent line to the curve, well, the curve means a function. A function. Sometimes we use, okay, let me take it back. Curve does not have to be a function, all right? We're going to focus on functions, but the curve can be represented by equations. Oh, how I get 1.1? No, that's given. 1, 1 is given in the question. So we're talking about example 1. So 1.1 is a point given. because this question is too long. So that's why this point is given in the question. Okay, so we make a so the definition is the tangent line to the curve. The curve does not have to be, in this case, it's a function, all right? Just in this case, it's a function. Imagine a circle is also a curve, all right? So this works for equations. Okay, the curve is right. The y equals f of x, limited to be a function, because we're going to focus on a function. But later on, when we talk about implicit differentiation, that works for every equation. At the point P, A, comma, f of A is the line through P, so with the slope m, limit x approaches A, f of x minus f of A divided by x minus A. Exactly the same with slope, all right? So provided that this limit exists. And we can write this in another way. Okay, so this is one way to write it, this way. And another way we can use h. We said, okay, we have 2 points. One point is A, f of A. Another point is the nearby point, very close to A. So we use h. So A plus h. H represents a number, very small number. So in the neighborhood of A. Then the function value is f of A plus h. So working with those 2 points, we can write the slope, in this case, f of A plus h minus f of A divided by h. Just another way of writing it. So think about the h is A plus h minus A, right? Because the second point, x2 is A plus h, x1 is A. To h, we're getting from A plus h minus A. All right, so 2 ways of writing this. But either way, we're working with 2 points. All right. So here we have 2 points, A, f of A, x, f of x. Right? X, f of x. So in this formula. But in this formula, we have these 2 points, A, f of A plus h, f of A plus h. And h we get from A plus h minus A. So that's why we can write it another way. And usually we use this one. Because this one is saying A plus h is very close. You see h approaches 0, right? In this case, x approaches A. Okay, that's the difference, x approaches A. But here we're saying h approaches 0, but they are exactly speaking for the same thing, right? Because h approaches 0, you see f of A. Right? Okay, let's see example 2. Example 2 is saying find an equation of the tangent line to the hyperbola y equals 3 divided by x at the point 3, 1. All right. So f of x, let f of x equal 3 divided by x. Then the slope of the tangent at 3, 1, we just use the definition. M equals to limit h approaches 0, f of 3 plus h minus f of 3 divided by h. Then we plug into f of 3 plus h and f of 3. F of 3 is 1. F of 3 plus h is 3 divided by 3 plus h, then divided by h. We simplify it. We rewrite 1 as 3 plus h divided by 3 plus h. So 3 minus 3 gets 0. We get negative h. Then divided by 3 layers. So divided by 3 plus h times h. Right? If you have 3 layers of fraction, we can just multiply the denominator, 2 denominators together. So this becomes h times 3 plus h. Simplify h with h, get negative 1 over 3 plus h. Now we can plug in h approaches 0. Right? So we get a negative 1 over 3. So we get a slope. Now we want to write the representation, the equation of the tangent line. So once we have slope, we have this point, it's easy, right? So we write y minus 1, basically y2 minus y1, right? Y minus 1 equals the slope times x2 minus x1. x2 is x minus x1, which is 3. Simplify a little bit, we can rewrite as x plus 3y equals 6 or minus 6 equals 0. So this is the equation of this tangent line, of this blue line, right? So this here, right here, x plus 3y minus 6 equals 0. So give us a function, give us any point of the function, and we can find the tangent line. We can find the tangent line, tangent to the point. Okay, we could use this for velocity problem. So average velocity is the same thing, equals the displacement, right, divided by time. Same thing, we can represent it with this, right? So let's see this example. Suppose a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. A, what is the velocity of the ball after 5 seconds? B, how fast is the ball traveling when it hits the ground? When it hits the ground, the height is 0, right? So what do? So we use the equation of motion. So that's, physics major that knows this. We use the equation of the motion. So S equals f of t, depends on time, equals to the 4.9 t squared. So velocity of A equals the limit h approaches 0, f of A plus h minus f of A divided by h. Just plug into the function. The input is A plus h, so we get 4.9 times the input A plus h squared minus 4.9 A squared divided by h. We expand this perfect square, so we get A squared, h squared, 2 times A times h. A squared minus A squared is gone. So we have 4.9 times 2AH plus h squared. And both terms has h. We can simplify that. We have 4.9 times 2a plus h. Now we have no problem to plug in h equals 0. Right, so 2a, so we have 2a times 4.9. We have 9.88. Right? So this a represents any point. For this case, it is, any point. Well, if A, then the question A is saying, okay, what about after 5 seconds? What about after 5 seconds? So after 5 seconds, we just find a V of 5. V of 5. You know what? Yeah, this A is okay, but usually think about this A is T, all right? But for the question does not use T, but A is to say, okay, this A is a number. A is a number. Okay, so V5 equals to 9.8 times 5. That's 49 meters per second. Okay, B, how fast is the ball traveling when it hits the ground? So we want to find the V, but the height now is 0. So since the observation deck is 450 meters above the ground, So the ball, when the ball will hit the ground at the time t1, which means S of t1 or f of t1 equals to 450, right? Set the function equals to 450. So that's our function, 4.90 squared equals to 450. Do the arithmetic. So t equals to about 9.6 seconds. So the velocity of the ball as it hits the ground is therefore 9.8 times this time we found, which is 94 meters per second. All right. Okay, any questions for this one? So the velocity will also use the limit, the idea of the limit. Because what is a velocity? Velocity is rate of change, right? Rate of change. So we use the definition of slope, rate of change. Okay, now, so this is very important. What is the derivatives? The definition derivative. We said the derivative means rate of change, right? It's a fancy name for rate of change. Now we make a definition of it. So make a definition. The derivative of a function f, derivative of a function f at a number a, denoted by f prime of a. So read this f prime of a. F prime of a is f prime of a equals to limit h opposed to 0, f of a plus h minus f of a divided by h. What is this thing? This thing, the slope of the tangent line at the point a, f of a, is called the derivative of the function at the point a. So those two things are equal to each other. One way we talk about the slope. Well, think about the slope, right? Slope of the tangent line. So this side is the slope of the tangent line. At a, f of a. Okay. So the derivative of the function at a, so this side, let me write here. The derivative of f of x at x equals to a. Okay, so this f prime of a is the derivative of the function at a, at x equals to a. And this side is the slope of the tangent line at this point. All right, so two things, if the limit exists, of course. Yeah, we talk about maybe you have this kind of, right? Then we won't be able to talk about the derivative. So talking about derivative, the function needs to be continuous. Let me write these notes here. So this is important. Okay, if the limit exists. Okay, let me see if I have any questions. Why did the write f prime of a? What does prime stands for? Oh, just a notation. Okay, later on we'll see different notations. We will see notations like this. df over dx, right? And sometimes we see y prime. Sometimes we see dy dx. They all mean the same thing, okay? They all mean the rate of change, of y in terms, or f or y in terms of x. Okay, it doesn't matter which notation they're using. I think this book and other books, right, they use different kinds of notations, but all those notation means the same thing. You think about a derivative, means rate of change. You know, it measures how two variables related to each other. So 1, 2, 3, and also we have f prime. Let me put f prime here. F prime of, okay, they all mean the same thing. They mean the rate of change of f in terms of x. How is x change affect f of x change? Okay, rate of change in between two variables. Okay, all right. So this definition is important, all right? So f prime of a, the rate of change of x, of f of x in terms of x at the point x equals a is the slope of the tangent line at a f of a. So make sure this, you know, two meanings make sense to you. Well, in another way, we can write this way: f prime of a equals limit x approaches a, f of x minus f of a divided by x minus a. Same thing, right? In this case, so here we have 2 points, a, f of a plus h, f of a plus h. Here we have the 2 points, f of x, f of x, a, f of a. But those two exactly mean the same thing. One is x approaches to a, one is h approaches to 0. One is seeing the difference of those 2 points approaches to 0. This one is seeing one point is approaching to the other point, but they mean exactly the same thing, just different way of writing it. Okay, now let's see example 4. We want to find the derivative of the function. This function is a polynomial function, it's a quadratic function, right? Polynomial of 2, degree 2. What is a quadratic function? At the number a. Okay, at any number basically. This a representing any number. So let's use a definition. So f prime of a equals the limit h approaches 0, f of a plus h minus f of a divided by h, right? This is the definition given. Just use the definition. Well, we plug in, so what is f of a plus h? Which is a plugging x into a plus h. So we get a plus h squared minus a times a plus h plus 9. Then minus f of x. Then we simplify, we see a, so perfect squares again. A squared plus 2ah plus h squared. Distribute negative a, negative ah plus 9. Now subtract a squared, subtract negative aa become positive, then subtract 9. Well, we simplify, we have a squared minus a squared. We have negative aa, positive aa, we have positive 9, we have negative 9. Well, what's left? 2ah plus h squared minus ah left. Every term has h, so factor h. Simplify with the denominator h, we have 2a plus h minus 8. Now we can plug in h equals 0. So h equals 0, we're left with 2a minus 8. Remember, we're treating a as a number. So now 2a minus 8 is just a number. So limit of a number, just a number, is 2a minus 8. If you give a some value, we can find out this we can find out what it is. Okay, let's see. Alexandra is saying, I think you can just take the derivative of each term, x squared to, oh no, yes, later on we're going to talk about a shortcut. Yeah, you are, you're getting ahead of us. That's great. But that's a shortcut. Okay, now we're going by definition. Let's analyze this. So we have f prime of a equals 2a minus a. Let me write in the term of x. So the function f of x equals to x squared minus ax plus 9. So that's the function, right? Now let's write its derivative. F prime of x, I'm going to write it in terms of x, equals to 2x minus 8. Let's compare these two functions. So if the original function is a quadratic function or polynomial degree 2, and its derivative is also a function, it's a linear function, it's degree 1. So for polynomial functions, there's a pattern. Its derivative function is always 1 degree lower. It's always 1 degree lower. All right. Okay. If we go through this later on, we're going to talk about second derivative. So this f prime of x is the first derivative. Second derivative, we can take a double prime. If we go through the same process, we do 2 times x plus h minus a, the minus, still we use the definition. We're treating f prime of x as a function. We find the derivative of this function, and we call second derivative. If we go through that, we'll get a 2. And see, this is a constant function. It's 1 degree lower than the linear function. So this is a pattern for polynomial functions. Okay, let's see the conclusion. The tangent line to y equals f of x at the point a f of a is the line through the point a f of a, whose slope is equal to f prime of a, and the derivative of f at a. Okay, this is exactly the definition. Okay, is exactly repeating this definition. And once we find the slope, so the slope is the derivative at the point. So we can write the tangent line as y minus f of a equals f prime of a times x minus a, right? y2 minus y1, slope m times x2 minus x1. Still the same process. Okay, now let's see another example, example 5. So let's find the equation of the tangent line to the parabola y equals x squared minus ax plus 9 at the point 3, negative 6. We already find this, right? We already find the derivative of this is 2a minus 8 from example 4. So now a equals 3. We just plug in 3. A equals to 3. So plug in to 3. So then what do we get? 2a, well, 2 times 3 minus a, negative 2. So the slope is just negative 2. Right? Then we use this point, we have this point. So I have y minus negative 6 become y plus 6. Negative 2 is the slope times x minus 3. We simplify this, we get a y equals to negative 2x. So the graph is like this. At the point 3, comma, negative 6, The tangent line is this blue line, is y equals to negative 2x. All right, any questions? All right, so this is how we find a tangent line at any point for any function, all right? But so far we don't know how to find a derivative of a function other than using this quotient. We call this a difference of quotient. It's the difference of quotient. We take a limit, right? So use this definition. And later on, we're going to introduce some shortcut. Okay, this is an important point. We're talking about rate of change. But more importantly, there's another word. It's called instantaneous. Instantaneous rate of change. So that's the marvelous function of calculus, right? Calculus, instantaneous rate of change, right? So at any point, rate of change at any point for nonlinear function. For linear function, right? The slope, slope is just a slope. Every point on the line have the same slope. But for nonlinear function, we have this curve. And the slope of the tangent line or the derivative at each point is different. So that's why we call instantaneous rate of change. So the derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. Okay, but just remember, derivative of a function is the instantaneous rate of change. That's it. It works for any kinds of function. Let's see this example. So let a d of t be the U.S. national debt at any time t. At time t, the table in the margin gives approximate values of this function by providing end-of-year estimates in billions of dollars from 1990 to 2010. Interpret and estimate the value of d prime. D of t is a function. D prime of 2000. So the derivative of d prime of 2000 means the rate of change of d with respect to t when t equals to 2000. That's the rate of increase of the national debt in 2000. So according to equation 5, hold on one second, that's equation 5. Oh, okay. This is saying equation 5, I think is the definition. Which one they call equation 5? Oh, it's this definition, right? So these are the 2 points. So take 2 points, right? 2 points, one point is x f of x, another point is a f of a. Use this equation, okay? Equation 5 is one of the definition. Take 2 points from the table, so we have d of t and t minus the point d 2000, so we have these 2 points. Then let's see, if t equals 1990, by 1990 we have this value. Then we do the calculation, you get 244.09. If t equals 1995, we get about this much, 2005. So this comes from the left, right? Think about the limits coming from the left. Then here is coming from the right to 2000. So coming from the left, it goes from 244 to 144. Coming from the right, it goes from 736 to 451. How do we make the conclusion? it said the table shows D prime of 2000 lies in between 140, about 140.04 and 451.70. So in between of those two. The left limit, right limit, not exact limit, but approaching to, right? So T approaches from the left, less than 2000, from the years more than 2000. So it's in between of those two. Then, so take the average value, then it's about 296. All right, so this is a rough example. Okay, now let's do some exercise. Let's use a definition, all right? Use a definition, practice using definition of derivatives. So let's try 4 and 6. So 4 and 6. You know what? 4 is cube. Cube is a, yeah, let's try 4 and 6. Okay, remember perfect cube. Let me write here, perfect cube. So x plus h increased by 3 equals to x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so this is called a perfect cube. To expand the perfect cube, it's the first one cube, the second one cube. Oh, missing 3 here. Then, oh, double 3. Then 3 times the first one squared times the second one. 3 times the first one squared times the second one. Then 3 times the first one multiply the second one squared. Right? It's by binomial theorem. Okay, let's try 4 and 6. I'm going to call people, or maybe you volunteer, or maybe I'd like to call some people today, especially those people haven't present yet. Okay, some people I don't see. I'm gonna call to make sure you're here because I see 25. So some people maybe use cell phones I don't see on the list. So if I call your name, that means I don't see your name. So Zara, Zahra. And Michael, Maikel. Moatasm, Moatasem. Euridia, Yuridia. Katie, Raymond, Carlos, JavokHir. I'm sorry, I don't know how to pronounce your name. Pandy. No, Karishima. Anna. Labiba. Labiba. Hillary. Nicholas. Ryan Nicholas. Oh, you're here. I'm sorry, I didn't see that. Thank you. Okay, this is a Mohara. I'm sorry, I don't know how to pronounce your name. Mokhira. Fedwa. All right, okay. Okay, anyone wants to show? I would take volunteers.
I'll try, Professor. The first
Okay,
one.
thank you. Let me make you a presenter.
Oh, I can't do the presenting thing. I can explain though, if that's
Okay.
fine.
Yeah. All right. Let's do that.
All right. So, for the first one, for number 4, for f of x equals x cubed minus 3x plus 1 at 2 comma 3, I use the difference quotient. Do you want me to explain every step as I input every number? Because that's a lot, or do you want me to go through
You can
mainly?
do quickly. You can do quickly.
Okay, so using the difference
Okay.
quotient, I just plugged in and I simplified it all the way through, and ended up getting the limit as h approaches 0, 3a squared plus 3ha plus h squared minus 3, obviously all in parentheses, and then that simplified through gave me 3a squared minus 3, and then I evaluated for a equals 2, and I plugged 2 in to that formula, which gave me 9. And then since f of x is the slope of the tangent line to f of x at x, that means we have m equals 9 at 2 comma 3. So then I plug 9 in to the formula y equals y1 equals m x minus x1, and then that simplified out gave me y equals 9x minus 15.
So y equals to let's use f of x. F.
Yeah, yeah.
You know what? Let's not confuse. Okay, let's use f of x. So the tangent line to f of x equals to. Can you repeat
9.
back to me?
I'm sorry?
Oh, can you repeat back to me? Let's use y.
Oh yeah, so my final result was that y equals 9x minus 15.
9x minus 15. Okay, thank you. Anybody has different answers? All right, great. Yeah, the steps are great. All right, that's it. Use the difference
Quotient.
quotient, then use the line formula.
Yeah. Thank you.
Okay, thank you very much, George. Anyone else wants to show 6?
It says
Oh,
Carlos
okay.
would like to do it.
Carlos, right. Carlos wants to do 6. Okay, go ahead, Carlos.
Hi. Yeah. So I'm gonna start with the quotient rule. Of 2x plus 1 and divided by x plus 2. So that will be there will be 2 parentheses x plus 2 minus 1 parentheses 2x plus 1 divided by x plus 2 to the power of 2, and we will extend the we will multiply the 2x to we'll get 2x plus 4 minus 2x minus 1 after simplifying everything over x to the second power plus 4x plus 4. So that will give us 3 to divide it or over x to the second power plus 4x plus 4.
Okay.
Okay, and then we will have y equals 3, 1 to the power 2 plus 4 plus 4. And we keep simplifying and that will give us 1 equals 1 over third. So that's the slope of the tangent. And then to get the line, we'll use the slope point form. Y minus y1 plus m per x minus x1. So we substitute now the ones for the y minus 1 equals the point that it was given, 1 over third, open parentheses x minus 1. And if we simplify, it will give us y equals 1 over third x plus 2 over 3.
Great, great. So your answer is writing as, let me see, I have x minus 3y or 3y minus x minus 2 equals 0, right? But anyway, let me follow yours. What's the line?
Y equals 1 over third x
1
with
over
3
third x
plus 2 over 3.
plus 2 over 3. I think it's the same. So I would like to write, let me see. I can write as 3y. Let's see if we have the same answer. 3y minus x equals to 2. Because I don't like to keep the fractions. Let's see, if we multiply 3 on both sides, right? We would have 3y, the minus x equal to, yeah, exactly the same answer. Okay. So that's for 6. All right, let's see. Alexandra wants to show different way. Okay, Alexandra, which one you want to show different way?
I didn't do necessarily the computation. I just did a rule that I knew when it came to dividing terms and finding the derivative.
Oh, that's something else. You're using quotient rule. We're
Yeah.
going to talk about it in the future. But
Okay.
sometimes, Alexandra, sometimes we want to use the definition because a lot of functions, we do not have a shortcut to find its derivatives. So then we're forced to use the definition of it.
Okay.
So for now, for this chapter, we just practice to use the definition. Does that make sense?
Yes.
Okay. All right, great. Okay, let's keep going. Anybody has any questions? So let's see in the exam, usually for the departmental exam, usually they have one question to require you to use the definition, to use the difference or quotient to find the derivative. So which means you have to go through this definition. This is a tedious way, but sometimes we have to use this one only way to find its derivative of function. But we will introduce a lot of shortcuts for polynomial functions, for rational functions. Okay, we don't have to go through this tedious way. All right. Okay, so section 2, the derivative as a function. As I talked before, right? Let's use a polynomial function. So f of x equal to the x squared is a derivative. We can go through the definition. So f prime of x equals to 2x. So the polynomial for polynomial functions, the derivative of the function is 1 degree lower than the original function. All right, that's for polynomial functions. But in any case, the derivative itself is a function. And if this is a cube, if the function is cube of x equals x cubed, later on we're going to use a shortcut. The derivative is 3x squared. It's a function, so it's a family of functions. It's a function, right? Give x any value, we can evaluate the slope of the tangent line at the point. But in any case, okay, so f prime of a equals the limit of this by the definition. So we can write f prime of x, a representing numbers, so x is the variable. We can write in a variable sense. So derivative are functions. So we can take a derivative of this function, and we call second derivative. And we can treat a second derivative of a function. We can take a derivative of the second derivative. We call a third level of derivative, so on and so forth. Okay, let's see this example. So this example is in the graph of a function f is given in this. So this is a polynomial function, right? How many wiggles? 1 wiggle, 2 wiggle, 3 wiggles. So we know this is a polynomial function of degree 4 according to our pre-calculus class knowledge, right? So this is a polynomial degree 4 function, polynomial of degree 4. And also you see the end behavior is upwards, right? So it looks like a W. And so we know the coefficient of the leading term is positive. So this is something we can read off. So leading term and read off from this graph. Is my screen moving? No? Oh, really? Did you see I'm writing on the oh, there's no new writing. Okay, Anastasia, maybe you refresh your screen or something, because other people can see my writing. So the example 1 is asking the graph of function is given here, right? This is a fourth degree of polynomial with leading term positive. And then if we want to figure out more, we have 2 roots here. two roots here, and we have y-intercept, we can write exactly what this function is, right? But let me not do that. You may try yourself. So we can estimate the value of the derivative at any value of x by drawing the tangent at the point x f of x, right? It's easy to draw a tangent line. Right? Let's think about at this point, we can draw a tangent line like this. At this point, we can draw a tangent line like this. At this point, you can draw a tangent line like this. At this point, you can draw a tangent line like this, right? The slope of those lines are derivatives at the tangent point. Slope of this tangent line is the derivative of the function at this point, so on and so forth. So if we do that, we see this. Okay? We see slope at this point is 0 because it's a horizontal line, right? Horizontal line, the y value are the same, so y2 and y1 are the same. When we subtract them, we get 0. So horizontal, horizontal, horizontal. Those are the relative minimums. At this relative minimum, this is relative minimum, relative minimum, relative maximum. And slope of those lines are positive. And slope going this way are negative. Right? So on and so forth. Slope this way are negative. So then, if we have this point, we have all those different kinds of slopes. And if we want to draw the graph, the slope function has this graph. It increases up to 1. So here, the original graph goes this way, going this way. And the slope, if we can draw another one, you see negative slope, negative slope, negative slope, negative slope, but the slope becomes bigger, 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 and bigger, and then becomes 0, then become positive, the slope become positive, right? So that's why we see this slope increasing up to 1, up to 1, up to probably this point. Up to 1, the slope from negative, 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 negative up to 0, then up to positive, 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 up to 1. Then after 1, if we can draw the slope, I'm not quite sure if I do that. It becomes smaller, smaller, and smaller, then goes to 0 again. So that's why after 1, the slope function gets smaller, smaller, smaller. Right? Then becomes 0, then after 0, the slope becomes negative again. Negative, 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 then becomes 0 again. Negative at a certain point somewhere here. Somewhere, and in the future, we're going to call this the inflection points. Maybe around here. All right. The second derivative will give us these inflection points, but I'm ahead of myself. Just draw as many tangent lines as possible to understand this. Okay, the slope function and the original function. So the slope gets smaller, smaller, smaller. All right. Then we have these inflection points. The inflection points, then the slope become bigger, 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 and bigger. All right. Okay. Original function, slope is another function. As we could see here, right? My example. If we polynomial degree 3, then its derivative is polynomial of degree 2. It's another function. We can draw this function. We can draw this function as well. Let's see this example. If f of x equals x cubed minus x, find a formula for f prime of x. Okay, be illustrated by comparing the graphs of f and f prime. go through the formula, go through the definition. So the cube, we have a perfect cube, right? Expand, cancel out some terms. In the end, you see the pattern. F of x always get cancelled from f of x plus h. Right? You see in this case, x cubed cancelled. So this part is the function part. X cubed, then x term cancelled. What else? There's two terms in the original function, x cubed minus x. So both terms being cancelled. So also the left terms, everyone has h as a factor. It divided by the denominator h. So we always get a lower degree. So this is a polynomial of degree 3. You see its derivative function is a polynomial of 2 degree. Right? Cubic function is derivative is a quadratic function. All right, now let's compare f and f cubed. If we graph f, right, x cubed will have 2 wiggles. Polynomial 3, 2 wiggles. It's this. And then if we draw the derivative function is a quadratic function. If it's a quadratic function, when we draw the quadratic function, we get this. This thing, the slope up to zero, the slope getting bigger and bigger. Getting smaller and smaller. You see, right? Getting small and small. Oops. To understand the slope, just draw the tangent lines. Right. Then after zero, this inflection point, the slope becomes bigger and bigger. So after this point. So that's why we see the slope function is a quadratic function. It goes this way. Example 3, we have square root of x. So let's find its derivative. Let's go through the definition. Go through the definition, we multiply by its conjugation to get rid of these square root signs. So in the end, we get the function 1 over 2 radical x. So the slope itself is a function. So we can draw both functions. Square root of x, x has to be at least 0. So the domain starts from 0. So this is the graph of square root of x. And we graph this 1 over 2 radical x, we get this graph. Get this graph. This graph is saying the slope function decreases, right? Decreases. Okay, let's say example 4. We have this rational function. Let's find its derivative to see the graph. Tedious calculation. After the calculation, we get derivative function as negative 3 over 2 plus x squared. Let's see the graphs of those two. Oh, we don't see the graphs. Okay, anyways, oh, okay, this doesn't offer graph. But if you want to find out, you can graph this on the decimals, all right? Okay, so this is going back to notations. F prime of x, y prime, dy dx, df dx, or sometimes we write it d dx, f of x. Or later on, this is for vector calculus class. Okay, vector calculus class where the derivative is a matrix, so we use a big letter D. But for us, for this book, we equal all those signs. Okay, they all mean the same thing. We shouldn't put those two here. Those two have different meanings. But anyway, we are treating how many? 1, 2, 3, 4, 5. Those 5 different notations means the exactly same thing. It's the instantaneous rate of change. The instantaneous rate of change of f in terms of x. All right? All of them mean the same thing. the limit of this. So this makes better sense because dy dx, what is dy? dy is a change in y. Think about y2 minus y1. What is the dx? X is a change in x, x2 minus x1. Then let one point be the other point. All right. Okay, let's see this one. Definition: a function f is differentiable. Differentiable means we can take a derivative, right? Can be differentiated. A derivative exists. If derivative exists, requires a limit exists. If a function f is differentiable at a at a point, if f prime of a exists, it's differentiable on an open interval, right? If it's differentiable at every number in the interval, right? Differentiable or polynomial functions are differentiable at every point. Square root of x is differentiable after x equals 0, because x cannot be 0. Right? Derivative will be 0 in the denominator. Okay, this is important. If we can take a derivative of f at a certain point, that means f is continuous at the point. All right? Otherwise, so f has to be continuous at the point. Otherwise, we won't be able to talk about derivatives. Remember, let's see if we have this situation. If we have a function like this, at this point, we have a vertical asymptotes. That means the limit does not exist. Left limit and right limit does not agree with each other, which means the limit exists, not exist. If limit does not exist at this point, we won't be able to talk about differentiation. There's no rate of change. All right. Okay, how can a function fail to be differentiable? The couple of situations. This situation we know, the second situation B, right? The limit does not exist, so we won't be able to talk about derivatives. And another situation is this, because remember when the slope, what's the slope of a vertical line? Undefined, right? So this kind of point introduce a vertical line, vertical tangent line. So this vertical tangent line, the slope is undefined. So at the point, we won't be able to talk about derivatives. Because why? Because the tangent line is a vertical line and the slope is undefined. Another situation we call corner or cusp. It's like this. It's a sharp corner. We call cusp. So here we won't be able to talk about derivative either. Because think about it, if we extend this a little bit, right? If we extend this a little bit, we see the tangent lines go to two directions. So at one point, we have two tangent lines. We have two tangent lines. So which one to follow? So that's why these three situations. Okay, limit does not exist. We won't be able to talk about derivatives. And if the tangent line at the point is a vertical line, we won't be able to talk about derivatives at the point. If the point is a cusp, sharp point, we won't be able to talk about derivative. All right, so those three situations fails to have a derivative of function at the point. Also, another one is the absolute value function. Think about the absolute value function. We also have this vertex. So absolute value function, we have this vertex, right? This is also cusp, this vertex. We won't be able to talk about derivative because one way goes this way, another way goes this way. So at this point, we have two kinds of tangent lines. Which line to follow? So it's undefined. So 1, 2, 3, 4, 4 situations. Would the removable discontinuities fall under this? It depends. It depends. Let's see. Let's see if we have. It depends. It depends on which situation. If removable fall under this first one, second one, and the third one, it still won't be able, right? But if it falls with a polynomial, that's fine. If it falls anywhere as a polynomial, that's fine. So it depends on each situation. If the removable discontinuity happens at this vertex, at this cusp, as at this, it still won't be able. All right. Okay, now higher derivatives. As I talked before, we have all the, so derivative itself is a function. I'm going to use a short notation, f prime of x, right? This function, we can talk about its second derivative, so original function is f of x. We can talk about its first derivative, second derivative. We use double prime to represent that. We can talk about this third derivative, so on and so forth. We can talk about its higher derivatives. Usually we use, then after that we use this, maybe fourth derivative. All right, f raised by 4. It's kind of strange. But let's talk about double derivative. So one way you can write as f double prime of x. So basically we're treating f prime of x as a function now. So take derivative with this function. So take derivative with f prime of x. And the process is the same. Right? So if our original function is x cubed minus x, and its derivative is 3x squared minus 1, we go through the same process. We find the double derivative is 6x. And then another way of writing it, sometimes this is, another way of writing it, we have dy dx. Then we take a derivative, treating this as a function. We're taking derivative of this function. So we write as a d dx. d dx of this. Then we can simplify as d squared y and dx squared. So this is just another notation for f double prime. Same thing for velocity, right? Talking about velocity is a derivative of displacement function. And then we have acceleration. Acceleration is a derivative of the velocity function. And it's a it's a second derivative of the displacement function. When do we use different notations? It depends. Depends. Let me think. Some people prefer to use this notation because this gives, f double prime doesn't tell people anything, right? But this d dx make more sense for some people. For myself, I prefer this set of notation. It's easier. I'm just lazy. I don't want to write anything more than I have to. But if you want to use this notation, you have to keep writing this, right? When you go to third derivatives, you have to do d dx again with this. But sometimes it may be more direct. It's telling you, this is rate of change of one variable in terms of another, right? This is direct. Really, you see, any situations it's mandatory for you to use this notation? I don't think so. I think none. It really depends on your choice. Okay, so people writing y raised by nth level of derivatives. So f, like I wrote f of 4 derivatives, or dny dx n. It's just notation, okay, just notation. If it's nth level derivative, you're just treating n minus 1 level as its original function, and that's it. So let's see this one. F of x still x cubed minus x. We want to find the third level derivative, so f triple prime. Then fourth level of its derivative. So the first level of derivative is 3x squared minus 1. Then second derivative is 6x. If we go through the same process, and the third level will be 6. Then when we take a derivative, we didn't really talk about this one. For any constant function, it's 0. Its derivative is 0. Right? Think about a constant function, right? We have x1, we have x, 6. We have another point, a, 6, right? For any point, the y value is 6 because it's a constant function. And when we do the derivative, we have 6 minus 6, we get 0. So constant function derivative is 0. This is different from the limits, right? Constant, derivative of a constant. But make sure you don't get confused with another one, the limit. What's the limit of a number? What's the limit of a constant? Limit of constant is a constant, right? Some students get confused with those two concepts. Limit of a number is a number, but derivative of a constant is 0. Because what's the rate of change? Imagine the function is a straight line, horizontal line. What's the rate of change of y value in terms of x? It doesn't change because it's a constant. That's why rate of change is 0. But when we take a limit of a constant, limit of 1, doesn't matter x approaches to anyone because it's independent of the x. So it's the constant itself. So make sure you differentiate those two concepts. All right, let's do some exercise. Okay, let's try 35. And 36. And 36. So basically find the points f is not differentiable. Okay, find the points which f is not differentiable. 35 and 36. If some of you came late, because I checked attendance already earlier, if you came late, let me know, because otherwise I have marked you absent. Okay, do I get volunteers for showing 35 and 36? Okay. I'm sorry, I don't know how to pronounce your name right. It's Lin or Hen?
It's
Oh.
hidden.
I'm sorry, Henan.
Yeah.
Okay, Henan. When do we use that? What do you mean? When do we use what?
Oh, you explained it already before.
Okay. Okay, Stanley wants to do 35. Okay, Stanley wants to do 35. Anybody wants to try 36? Okay, Stanley, go ahead.
There's a -1 is not differentiable because it's a vertical tangent.
Great, okay.
And then 4 is also not differentiable because it's a corner.
Right. Okay, Henan wants to do 36. Great. Go ahead.
It is not differentiable at -1 because it's discontinuous, and then also at 2 because there's a sharp point. So
Right. Any other points? Yeah, only 2. Yeah, for 36. Okay. For 35, we have 2 points at the -1 because this is, later on we'll call this inflection points. Okay, the second derivative equals to 0. So this at this point the tangent line is vertical, right? We know the slope of a vertical line is undefined. So at the point, so -1 is not differentiable. And what about this? So at 4, it's a cusp, it's a corner. So this one is not differentiable. For 36, we say again, -1, we have a problem. -1, the limit does not exist, but the definition of derivative is the limit. So if limit does not exist, the function is not differentiable at the point. Also, we see this corner, the cusp, is not differentiable. All right, let's see what else. Maybe. Okay, I think we have time. We have 2 minutes left. Let's go through this. So basic differentiation formulas. Derivative of any number equals 0 because we have the number subtract the number equals 0. Okay, derivative of constant is 0. It's different from limit. Again, okay, limit of a constant is the constant. And derivative of x is 1 if it's an identity function, right? It's 1 because we have the same thing divided by the same thing. I have derivative of x squared equals 2x. So I think Alejandra was talking about the shortcut. This is by shortcut, all right, quick way. So taking derivative of x squared, we get 2x. Derivative of x cubed, 3x squared. We can go through this quotient formula by definition. And the derivative of x raised by 4 equals 4x cubed. So let's see the trend. X is 1. So what is the exponent of 1? It's x, right? So x squared, exponent is 2. So get 2x. X cubed, exponent is 3. We have 3x squared. And the x4, we get 4x cubed. So what is the trend? What's the shortcut? The shortcut is saying derivative of any polynomial is the coefficient is the exponents. So the exponents become the coefficient in the derivative function. And the degree reduced by 1. And this is called a power rule. Okay, the power rule works for polynomial or polynomial-like. Polynomial-like. Okay, this n can be any integers. Okay, can be any integers. You see, we move the exponent to be coefficient, then we subtract 1 from the degree. So let's go back to this. The degree x here is 1. So 1 multiplied by x, then 1 minus 1 equals 0. X raised by 0. That's 1. 1 times 1 is 1. For x squared, we move 2 to be the coefficient. Then 2 subtract 1 is 1, so get 2x. X cubed, move 3 to be the coefficient. Then 3 minus 1 is 2. 3x squared. For x raised by 4, 4 becomes coefficient. Then 4 minus 1 is 3, 4x cubed. So this is called a power rule. All right. If you like, you can go through this proof. So let's see some examples. Function equals x6, then derivative is 6x raised by 5. It's t raised by 4, is 4t cubed. If x raised by 1,000, that becomes 1,000. Derivative is 1,000, x raised by 999. The r cubed becomes derivative is a 3r squared. Power rule, right? Well, let's see this. This is a polynomial-like. So 1 over x we can think as x raised by -1, right? So dx of x raised by -1. We can write it as polynomial-like. Then, so we move -1 to be coefficient. So we get negative. So equals to negative. Then x raised by -1, -1 minus 1 becomes a -2. So that becomes negative x raised by -2, or -1 over x squared. So polynomial like, so power rule works for any polynomials and polynomial-like. That's for 1 over x, like the right here. Okay, we don't need this. And take derivative of square root of x, we can write square root of x as x raised by half. Then we use the polynomial rule. So half becomes coefficient. Minus 1 from half, we get -half. So that's why earlier we see derivative of x, square root of x is 1 over 2 square root of x. All right, so this is shorthand rule. Okay, so polynomial power rule. And we can differentiate 1 over x squared. We can write as x raised by -2, right? X raised by -2. Then -2 becomes coefficient. Minus 1 from -2 becomes -3. So it becomes, so derivative of x raised by -2, or 1 over x squared, is -2 over x cubed. Similarly for this, we can write as x raised by 2 over 3. 2 over 3 become a coefficient. Minus 1 from 2 over 3. We have 2 over 3 x raised by -1/3. And we write this as a 2 over 3 cubic root of x. All right, so that's power rule. And with that, we can find the equation of tangent line at any point, right, for any polynomial-like functions. The process is the same. Derivative at this point, derivative of this function is a function. At this point, we can evaluate its derivative, then become slope of the tangent line. Then we use this point to write the tangent line formula, the tangent line equation. If the function, so for any, so this is a scalar, right? C. If it's a scalar, we can always factor out the scalar. Let's say this one. So if the function is 3x raised by 4, we can factor out 3. Let's say just take a derivative of x raised by 4. Then we have 4x cubed, then times this 3 becomes 12x cubed. Well, normally we do this. We do 3 times 4, we get 12 right away. Then subtract 1 from 4, we get 3. All right, scalar remains to be a scalar. And the addition works, okay, if the derivative of a sum of two functions is the sum of two derivatives. Works for subtraction. That's why for this polynomial function, right, we just differentiate each term, each term, each term. But we don't have to really write this way. Okay, derivative of a sine function is a cosine function. Derivative of a cosine function is a negative sign. Derivative of cosine is negative sign. Yeah, you can go through this definition, okay? This is all getting from the definition, go through the definition. If we differentiate this, y equals 3 sine theta plus 4 cosine theta. Sine derivative is cosine, so we get 3 cosine theta. Cosine is negative sign, so we get minus 4 sine. And so if we do that, you see after 4, right? So this is cyclic. So going back to sine. So for, right, you can just go through this. So f of x equals cosine. F prime equals negative sine. F double prime is equals negative cosine because sine is cosine, get negative cosine. Then cosine is a negative sign. The negative and negative become positive. So 4, right, cyclic of 4. So for f raised by 24, so what is the level of 24 derivative? We divide it by 4, that's 0, which is cosine x. For 27, we divide it by 4, the remainder is 3. Remainder is 3. So going back to sine. All right, we're going to talk about more examples for this. So for your homework, it's 2.1, but you may try 2.2 also. All right, okay, any questions? Can we go over 2.3 next class real quick before other topics? Sure. What's 2.3? Oh, that's 2.3, right? 2.2, 2.3. Yes, of course. Okay, any other questions? All right, I see you Thursday then. Okay, thank you guys. Do the homework. Let me stop you.